December 24th, 2024, 11:53 UTC. A spacecraft the size of a car flew directly into the atmosphere of the sun. Every power grid on Earth, every satellite above your head, every communication system your civilization runs on. What happened next concerns all of it. But for thousands of years, every culture that looked up at the sun called it one thing: untouchable. Not a machine, not a problem to be solved. A god. It is not a god. It is a loaded weapon pointed directly at our civilization. And on Christmas Eve, we flew inside it for the first time in history. We touched a star. Most people assume the sun is dangerous because it is hot. And yes, the surface burns at around 5,500 degrees Celsius. That is already hotter than anything most people can conceptualize. But here is the thing. The surface is not the dangerous part. The dangerous part is the corona. The corona is the sun's outer atmosphere, a massive invisible envelope of plasma extending millions of kilometers into space in every direction. And the corona is not just hot, it is shockingly hot, inexplicably hot, offensively hot. The corona reaches temperatures between 1 and 3 million degrees Celsius. That is up to 300 times hotter than the surface directly below it. If you stand next to a fire and walk away, the cooler it gets. That is the most basic law of thermodynamics. Yet the sun does the exact opposite. Physicists have called this the coronal heating problem, and for more than 80 years, it was one of the greatest unsolved mysteries in all of astrophysics. But the coronal heating problem is not just a scientific curiosity, because it is from this corona that the solar wind is born. A relentless stream of charged particles blasting outward from the sun in every direction. It travels at speeds between 300 and 800 kilometers per second. That stream reaches Earth. It hits our magnetic field, and when it hits hard enough, it creates geomagnetic storms. These storms knock out satellites, they disable GPS systems, they overwhelm entire power grids. Understanding the sun is not an academic exercise. It is about protecting what civilization runs on. Before we get to the mission itself, there is a story you need to hear, because the spacecraft is named after a person, and that almost never happens. In 1958, Eugene wrote a paper. He argued the sun emits a constant stream of charged particles outward through the entire solar system. He called it the solar wind. When he submitted the paper, the editor sent it back. The peer reviewer wrote that it contradicted established physics and should not be published. Parker appealed. The journal eventually published it, only after the intervention of Subrahmanyan Chandrasekhar, who would later win the Nobel Prize in Physics. 4 years later, spacecraft measurements confirmed that Parker was completely right. The solar wind existed exactly as he had described it. And over the following decades, Eugene Parker became one of the most important figures in solar science. NASA prepared to launch a mission into the sun. They did something they had never done before. Parker was 91 years old when NASA made its decision. They named the spacecraft after a living person. Here is the engineering problem that kept physicists awake at night for decades. How do you build a spacecraft that can function inside a star? The shield exterior reaches around 1,370 degrees Celsius during close passes. That is hotter than lava. That is hot enough to melt steel, aluminum, titanium. And yet, the scientific instruments sitting just behind the heat shield operate at roughly 29 degrees Celsius, room temperature, through a piece of material that is only 11.5 centimeters thick. The solution is one of the most elegant pieces of engineering NASA has ever produced. The heat shield is made of two panels of carbon-carbon composite sandwiching a core of carbon foam. That foam is 97% air, light, extraordinarily strong, and one of the most effective thermal insulators ever flown in space. But here is the part that surprises most people. The corona is 1,000,000 degrees, yet the spacecraft does not vaporize, because in a near-perfect vacuum, even a 1,000,000-degree temperature delivers almost no actual heat. The plasma is so sparse, so few particles strike the shield. The heat load remains manageable. It is not swimming through fire. It is surviving the void between the flames. And there is one more challenge almost no one talks about. The forces trying to tear the spacecraft apart are immense. At 692,000 kilometers per hour. The engineers designed flexible joints that allow the frame to flex rather than resist, designed to bend, so it would not snap. Parker's solar probe launched in August 2018, but it did not fly directly toward the sun. It could not. The gravitational geometry of the solar system makes a direct approach essentially impossible. A spacecraft launched from Earth carries too much orbital velocity. It would overshoot into a wider orbit rather than falling inward toward the sun. So NASA used a technique called a gravity assist, using the gravitational pull of another planet as a slingshot. And the planet they chose was Venus. Over 6 years, Parker's solar probe flew past Venus 7 times. Each flyby used Venus's gravity to bleed off orbital speed. It pulled the spacecraft's orbit tighter and tighter around the sun, like slowly reeling in a fishing line. With each orbit, the spacecraft reached a new record-close approach, then fell inward again, closer than before. And during those 6 years, it was already making discoveries. The solar wind near the sun was far more complex and turbulent than anyone expected. It detected strange zigzagging reversals in the sun's magnetic field, structures scientists nicknamed switchbacks. They appeared in far greater numbers than predicted. They also seemed to play a key role in accelerating solar particles to remarkable speeds. It flew through enormous coronal mass ejections, those massive explosions of solar plasma. It measured them from the inside for the first time in history. The final Venus flyby happened in November 2024. After that, there was nothing left to do but wait for Christmas Eve. That morning, the team at the Johns Hopkins Applied Physics Laboratory in Maryland was not celebrating the holiday. They were sitting at their consoles waiting for their spacecraft to disappear, watching telemetry data, watching the line go flat. As Parker's solar probe fell toward closest approach, it entered a communications blackout zone. The corona's electromagnetic radiation completely overwhelms any radio signal the spacecraft can transmit. The team knew this was coming. They had planned for it. But knowing something intellectually and experiencing it are very different things. At some point during that Christmas Eve, their spacecraft went silent. A machine they had spent more than a decade designing and building, nursing through 6 years of progressively closer orbits, went silent. Completely unreachable. No telemetry, no beacon, nothing. There it was, 6.1 million kilometers from the surface of the sun, moving at 692,000 kilometers per hour, flying on autopilot through the atmosphere of a star, with no ability to receive commands or transmit data. For comparison, Mercury never gets within 45 million kilometers of the solar surface. Parker's solar probe was more than 7 times closer to the sun than Mercury ever gets. On the evening of December 26th, the Mission Operations Center received what they had been waiting for. 2 days after closest approach, a beacon tone. just a simple radio signal indicating the spacecraft's health status. It said, essentially, I am here. I am operational. Everything is working normally. The room erupted. Engineers who had spent years of their careers on this mission were openly emotional. On January 1st, the full telemetry data began arriving. 2025. Researchers finally had something they had never had before. A detailed view of the sun's corona. Not from a telescope pointed at it from millions of kilometers away. From inside it. The spacecraft's whisper camera captured footage of the solar wind being born. You could see the streams of plasma pulling away from the corona, accelerating outward, organizing themselves into the patterns that eventually reach Earth. Scientists described it as watching a river at its source, after spending decades only ever observing it hundreds of kilometers downstream. Suddenly, the entire dynamic of how solar weather forms became visible in real time. The data also captured something that had only been predicted theoretically before. A phenomenon NASA scientists are calling the solar wind U-turn. When the sun launches a coronal mass ejection, not all of the material escapes into space. Some of it loops back toward the sun, pulled by the sun's own magnetic field. It alters the corona and influences the path of the next ejection. Parker's solar probe filmed this directly, up close, in detail no one had ever seen before. Understanding this feedback mechanism is critical for improving space weather forecasts, because it helps explain why some solar storms are far more powerful than others. And then there is the coronal heating mystery itself. The data is pointing toward those switchbacks as one of the primary mechanisms. Those zigzagging magnetic reversals transfer energy from the sun's surface into the corona. It is not one single process. It is a complex interplay of magnetic reconnection events and turbulent wave activity. And Parker is giving scientists the resolution they need to finally map it. 80 years of mystery may be close to having an answer. Parker's solar probe has continued making close approaches throughout 2025, each time matching its record distance of 6.1 million kilometers, each time moving at 692,000 kilometers per hour, right through the peak of the sun's 11-year activity cycle. Step back for a moment. Think about why this actually matters in practical terms. Every major solar storm gives satellite operators between 15 minutes and a few hours of warning. That is barely enough time to put satellites into safe mode, let alone protect large power infrastructure. A sufficiently powerful storm could trigger cascading failures in power grids across entire continents, one comparable to the 1859 Carrington event. Some estimates suggest recovery could take months or even years, at a cost that would make almost any natural disaster in history look minor. The data Parker Solar Probe is gathering is the foundation for building genuinely reliable early warning systems. Seeing how solar wind forms at its source, how coronal mass ejections behave before they travel to Earth. Instead of 15 minutes of warning, we could eventually be talking about days. That difference is not just scientifically interesting. It could protect trillions of dollars of infrastructure and millions of people who depend on it every single day. December 24th, 2024. A machine built by human hands flew into the atmosphere of a star. It survived temperatures that would vaporize any ordinary material. It moved faster than anything we have ever built. And it came back carrying data that is already rewriting textbooks. For thousands of years, the sun was something we were forbidden to approach. A god, a mystery, a force beyond human reach. The sun is still a loaded weapon, but for the first time in history, We are learning how to read it.